Today we're going to be talking about modeling real-world applications with logarithmic and exponential equations. There are two formulas we're going to use: compounding continuously and then your compound rate or compound interest formula. Compounding continuously is also known as PERT, where A is equal to P times E being a number, which is approximately 2.718, to the power of R times T. For what P, R, T, and A stand for, you can look on the left here. I want to tell you real quick, A is your complete total amount. So this is after you plug in PERT, that's your total amount for A. Alright, the compound interest. The only difference is N. N in this formula is a number per year. So, excuse me, I'm sorry. So you have it annually, N is equal to 1. If it's biannually, 2. If it's every quarter, 4. If you have it 5 times a year, N is 5. You get the idea. The one thing I want to point out for compound interest formula is there is a plus and minus inside the parentheses here. You use the plus if the equation is exponential growth or increasing. The minus is for decay or decreasing. Alright, let's start some examples. A substance decays 22% each day. After 7 days, there are 9 milligrams of the substance remaining. How many milligrams were there initially? You are not using PERT on this because you do not see the word continuously. Continuously is very important. That tells you if you use PERT or if you use the compound interest formula. This one is the compound interest because continuously is not in the question. So, we have, if my pen will work, we have A, R, N, and T to identify. Wait a minute, and P. A, your N value. This says there are 9 milligrams, so A is 9. Your rate is decaying by 22%, so this is 0.22. Your N value is 1. Notice this is not per year because we're not dealing with years, we're dealing with days. This says each day, so it's 1 day, and is 1. Your time, we want to know how long after 7 days. The principal amount, it is not given, that's what it's asking us for. I'm going to put a question mark. So we're going to have 9 equals something times 1, this is decay, so minus 0.22 to the power of 7. We're going to divide this over on this side. So instead of writing 1 minus 0.22, I'm just going to write 0.78. So 0.78 to the 7th. It's the same thing. 0.78 to the 7th. If we type this in Desmos, we get 51.237 approximately. So our p-value is approximately 51.237. And this is in milligrams. Alright, question number 2. Sam opened a bank account with an interest rate of 4.8% that is compounded annually. He invested that much in 1999, made a withdrawal in 2007. How much money is in 2016? This again is the compounded interest. So we're going to have our initial amount, A equals our initial amount, 3,890. We are multiplying this by 1. This is growth, so plus our rate of 0.048 over 1, because this is compounding annually. So it's every year. Sorry, y'all. I don't know why I'm coughing so much. Alright. For T, we're trying to find out how much in 2016. But before that, he's making a withdrawal in 2017. So we need to figure out how much money he has at 2017, so we know how much money, after he withdraws it, how much money he has left, okay? So from 1999 to 2007 is 8 years, so it's 1 times 8. Now if we type this lovely number in Desmos, $3,890, 1.048 to the power of 8, I think. Yep. Oh. 5660.31, approximately. This is dollars, and this is in 2007. He is taking this number, and he's making a withdrawal of $2,300. So this is going to leave us $3,360.31. So for 2016, we have our amount is equal to, our new initial amount is this number, 3,360.31. Everything else is staying the same, so 1.048. Alright. Your time in this problem from 2007 to 2016 is 9 years. If you put this in Desmos, you're going to get approximately, and let's find out. $3,360. $51.24.26. $51.24.26. There's our final answer. How much more money would Sam have in his account in 2016 if he hadn't made the withdrawal? You can do this yourself. The only thing they're going to change, use the first equation. And by first, I'm talking about this one. Change your 8 to 17. I'll tell you how much you got. And that number is going to be approximately 8651.60 without any withdrawal. It says how much more money. I'll underline too far. So we're going to take that number, subtract your 51, 26, 24, 26. And you're going to get $3,527.34 more if he had not had to make the withdrawal. Alright, that was fun. Moving on down the line. In 1963, the number of cars in the United States was 1.7 million. By 1988, it had increased to about 2.9 million, right an exponential function in the form y is equal to a times b to the x that could be used to model the number of cars, y, in millions. For 1963 to 1988, write the equation in terms of x, the number of years since 1963. Round the value b to the nearest thousandth. Or thousandth. Crap. Thousandth. There we go. So, our equation. Y is equal to ab to the x. Your a value, which is your principal amount, 1.7 million, so 1,700,000. That's 1.7 million. I just wanted to make sure I wrote enough. So, A is equal to that. We don't know the B. We do know X, because X is the years between 63 and 88. So 1988 minus 1963 is equal to 25, which is our X value. Your Y is 2.9 million. 2.9. There we go. 2,900,000. 2,900,000. There we go. Alright, time to find B. So we have our 2,900,000 is equal to your 1,700,000 times b to the x. X is 25, just kidding. Divide by your 17 million, or 1.7 million. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. There we go. Alright. This is going to simplify down to 29 over 17 is equal to your base to the 25th power. To get this base, you're going to take the 25th root. So, 25th root of 29 over 17 is equal to your base, which is approximately, and I have absolutely no idea. So let's find out. Your 25th root, well, let me type in this part first. 29 over 17. Your 25th root is the same thing as to the 1 over 25th power. So you get 1.02, approximately. We're going to write the equation now. And it's going to be y equals 1.7 million. Your base is 1.02 to the x power. There's our equation. We're finished. Suppose the number of cars continue to grow at the rate. Estimate the number 2005. I'm going to skip this. You can come back later if you want to try for yourself. I will go on and give you the answer. I'm going to let you try to work to it, though. You know what? I'll just go in and show you how I got that. You're finding your Y value. So you have your principal amount. You're multiplying by your 1.02. From 1963 to 2005 is 42 years. If you put this in Desmos, that's your approximate answer. Okay. I showed you, because I broke down. Come on. Let's move on. The number n of college graduates in thousands after t years can be modeled by n equals 46 log base 5 of t plus 3. Let t equal 0 represent 1985. How many college graduates were there in 2003? Here we go. This is probably the easiest one on the paper. Your t value. If t is 0 is 1985, to find t, we're going to do 2003 minus 1985 and get 18. 18 plus 3 is 21. Okie dokie. Desmos. We have $87.0167. I'm going to write down, these are in thousands, okay? I'm going to write down 87.0167. $87.0167. Is that right? 81.0167. Alright. In thousands, because that's your n value, in thousands. This is 87,000, not point, sorry. So 87,016.7 grads. Quick question for you to ponder. Can you have 0.7 of a person? The answer you should very quickly come up with is no. Here's your option. If you write this down, personally, I'm going to count this correct. Okay? I don't like it, but I'll count it correct. In my opinion, the answer to this problem is 87,016 people. I believe this would be a flooring function, just the mathematical name, meaning you drop the decimal point. That is my answer that I would give. However, some mathematicians would argue that once you start a new person, so after your 87,016, as soon as you hit 0.1, that counts as a full person. So I'll accept any of these three answers. Whichever one you like the best, makes the most sense to you, you can choose. I do not care. But really and truthfully, if we're going to, pick sides, and I am, because this is my lesson, I choose that one. But, whatever. How long until there are 123,000 college graduates? And when will this occur? I'm going to let you come back and do this later, after I do the last problem, just to shorten my video a little bit. Just so you know what you're trying to get to, approximately 70 years. I think. If I worked it out correct earlier and, memorized it. And so this will be a 2056. How long until graduates? Hold on, y'all. 2055. I'm thinking back and trying to think if I wrote down the wrong thing earlier whenever I did this problem. Because I think I wrote 2056. But 70 plus 1985 is 2055. Okay. When Angela was born, her grandparents deposited $5,000 into a college savings account paying 6% interest compounded continuously. Ignore this. You see this word continuously, you automatically think PERT. I should not have to give you this equation like I did, but I should not have to give it to you. What is the balance after 15 years? We're using the PERT formula. Just as a reminder, total amount is equal to your principal, E, which is not a variable, the number E, to your rate times time. That is a 6, not a T. Times time. Alright. It's asking what the balance will be after 15 years, so you're trying to find the total amount. Your principal amount is $5,000 times E. Your rate is 0.06. Your time is 15 years. $5,000 E exponent. Okay, I'm going to say first, this is incorrect. I'm about to type. I'm going to talk the exact buttons I hit, okay? It is going to be incorrect. I just want to show you because you have to be very careful. 0.06, and it says times 15. This gave us $79,637.74. This is incorrect. I cannot highlight on this screen, so I'm going to have to walk you through it. Look at your E. The exponent is just the 0.06. If you hit times 15, it will throw it back down into your, I don't know how to say it right, I guess your regular line. Make sure you have the 0.06 times 15 inside of parentheses, or it can give you an incorrect answer very, very quickly. So you get $12,298 and 2 cents. I have not a clue what I just said. 12,298. And 2 cents. Pretty fun, right? Almost done. How long will it take the balance to reach at least 17,000? Same formula. We're just changing one thing. Instead of looking for our total amount, we are given it, and we want it to be $17,000. We're asked to find how long, so we're looking for our time. The first step, we're going to divide by that 5,000 out front. That cancels out. So this is going to give us 17/5 is equal to E 0.06 T. We're going to take this base, shove it under the 17/5, add a log in front. So we're going to have log base E 17/5 is equal to 0.06 times T. We're going to divide by that 0.06. So you're going to get T is approximately 0.06. Make sure I did that right. Hold on. This is not looking right. I'm getting 17. I know I got 20 earlier today. I think I had 20 earlier today. You know what? Let's check it. 5,000 times E to the power. When I get close, 17 point. Well, ain't that interesting? Oh, my bad. I typed in 6. And it's supposed to be a 5. My apologies. So, log base E of 17/5 divided by 0.06. Approximately 20.40. So almost 20.5 years. Sorry about that. I knew I should have got 20 point something. But typed in the wrong number. Should have been 17/5, not 17/6. As a last side note before I conclude this lesson, if you saw what I typed earlier and paid attention, I typed the ln of 17 over 5. ln is the same thing as log base e. Don't forget that. Just want to remind you that's where it came from. Alright, I'm